Okay, implicit differentiation. Before now, we've been doing explicit differentiation. That's if one variable is written explicitly. That is, if you make one variable the subject of formula. Example, I think we always see that y is equal to sine x. We made y subject of formula. Maybe if you have y equal to x squared plus 3x plus. So here, y is written explicitly. But here, in implicit differentiation, we'll write both x and y together. Maybe if you have like x squared plus y squared is 5. Something like this. Or if you have xy plus cos x equal to 7. Something like this. So that's what we do here. And to solve this is very easy. We differentiate both sides. We introduce, and remember, we always differentiate with respect to x. So what we normally do is d over dx. So that's what you have to bear in mind. So look at these questions. We're asked to differentiate the following. So let's start with the first one. So they gave us that x squared plus y squared equal to 4. The first thing you have to do is to introduce derivatives with respect to x to both sides. So we introduce d over the x of x squared plus y squared, and also d over the x of 4. And we can see that the derivative of 4 is 0, so it's easy. Why here we can open up as the derivative of x squared plus the derivative of y squared. And you can see this is also easy. We know that it's 2x. But here, there is where the major work comes in. What we have here is y. Well, we are differentiating with respect to x. As you can see, this is simple, x. So how do you do this? As a mathematician, what we do is for this to be differentiable, for us to differentiate this, the variable here will be the same as this. So we introduce y. But to avoid changing the equation, because we've changed the equation now, this is the x and this is the y. But to counter it, that's to come back to it, we multiply by dy over dx. Do you see the logic? Because if you count dy, we now have the dx of y squared. So nothing has spoiled. This is just common logic. So our main aim is now to make, remember, we have to find dy dx. So we'll solve for dy dx. So we'll make dy dx the subject of formula. So here we can easily differentiate this now, because what we have here is dy. So plus 2y, because what you have here is now y, dy dx equal to 0. So making dy dx the subject of formula. So first of all, move this to be 2y dy dx equal to minus 2x. So dy dx, which is what we asked to find, minus 2x over 2y, which is minus x over y. So that's it. So whenever you are asked to find, that is to differentiate any implicit function, we introduce the derivative, which is d over dx, to both sides. We differentiate and now make dy dx the subject of formula. Okay, let's look at this one also, the second one. Okay, the second one, again, we start with what we did before. We introduce dx to both sides. Equal to d over dx of 10. So the same, we need to be okay, let's continue. Splitting this as d that plus the dx of y squared plus d over dx of 3xy equal to, okay, let's just write, we know it's 0. So we know that if you differentiate this is 2x. Here, remember, you have to introduce your dy to avoid changing the equation. So for now, we've known that is if you differentiate this 2y, you introduce your dy dx. We've done it before. We know why. That's the reason. We introduce dy and after counter it with dy dx. So that's why if you differentiate this 2y dy dx. Okay, see our major target here, because we've done something like this before. See this, because this one has xy, so we use product rule here. But before then, we can factor the 3 because it's a constant, so we can bring it out. Why this is 0? Okay, let's continue. So this is product rule, uv. So do you remember the derivative of that is, if you remember from our product rule, that if you have d over, that you should differentiate uv, where u and v are functions of s, is u dv plus v du. Do you remember product rule? So that's what we are going to use here. So we have u, our u is x and our v is y. So we have u, which is x, d over dx of y, plus our v is y, d over dx of x, equal to 0. Do you see the logic? We use product rule here. Our u is x and our v is y. So u, which is x, dv over dx, which is our v is y. So let's continue. We have 2x plus 2y dy dx plus 3. We'll multiply x dy dx plus dx over dx is 1, so plus y, equal to 0. So let's open up and make dy dx the subject of formula. We have 2x plus 2y dy dx plus, we'll open up, we have 3x dy dx plus 3y equal to 0. So we have this, so we'll factor. So we have 2y plus 3x dy dx. Do you get? This is 2y plus 3x. We'll factor dy dx. Why this and this goes to the other side to be minus 2x. Maybe let's factor it plus 3y. You get 2x goes to the other side to be minus 2x. 3y goes to the other side to be minus 3y. So making dy dx the subject of formula, we now have minus 2x plus 3y over 2y plus 3x. So that's it. So our target here is when we have products. The first one was just y, but this one has both x and y as products. So once you have anything like, please remember to use product rule. It's very important. So looking at the last one, we introduce our derivative to both sides. So we have that d over dx of sine cube x cubed plus y squared, and I have d over dx of x squared. We introduce dx cubed plus y squared, yes, so that we can differentiate this. So it's easy now, we can differentiate because what is here is here, but it seems we've changed the equation. And what do? We multiply by what? Because we want to bring this back, we multiply by dx cubed plus y squared over dx. We've moved it back to this, because if this cancels this, we have the dx of this. So it's just common logic. We have d over dx of x squared. So we can differentiate this now. So the derivative of this is, the derivative of sine is cosine. So we have cos x cubed plus y squared times the derivative of this. And again, the derivative of addition is the same as the derivative of the two, s cubed plus the derivative of y squared equal to, okay, let's differentiate. If you differentiate this, you have 2x. So do you see the logic? The dx of all this, we open up the dx of s cubed plus the dx of y squared. So we'll continue. We'll have cos s cubed plus y squared. The same. So we'll have 3x squared plus, but there is a problem here. This is x, so remember, we've done it before. So if you differentiate this, you have 2y. After, we'll counter it with dy dx. You know why? I've done it before. Equal to 2x. So our main aim is to find dy dx. So let's rule this. So remember, our main aim is to find dy dx. So we'll make it subject of formula. So we'll move this to the other side. So I have 3x squared plus 2y dy dx is equal to 2x over cos s cubed plus y squared. So we have 2y dy dx is equal to, this goes over to be 3x over cos x cubed plus y squared minus 3x squared. So I've moved this to the other side. Okay, this should be 2x. Sorry, this 2x. So the next thing is to divide both sides by 2y. So I have 1 over 2y divides 2x over cos s cubed plus y squared minus 3x squared, which is our answer. So it's a very tricky question.